Hello, my name is Musab and I will present you my abstract entitled Investigation of Sulfur-resistant Nickel-based Catalyst in the Dry Reforming Reaction of Biogas, Effect of Yuttrium, Cerium, and Magnesium Incorporation. The dry reforming of biogas is a very important reaction because it uses biogas produced from biomass as a feedstock. Also, it reduces the negative effects of the climate change, and besides it produces the hydrogen as a renewable energy resource. The main and the primary reaction of this process is the reaction of methane and carbon dioxide, which are the main components of the biogas in order to form carbon monoxide and hydrogen or cyan gas as shown in equation 1. Besides this reaction, some side reactions can also take place at the same time, such as the reverse water gas shift reaction shown in equation 2. The equation 1 is a very high endothermic reaction. That's why it requires high temperatures in order to overcome the activation energy of the reaction. For this reason, catalytic systems are used in order to reduce the need for the high temperatures and also in order to push the reaction towards the formation of carbon monoxide and hydrogen. In particular, nickel catalysts are used because of their high activity and cost effectiveness. However, nickel catalysts deactivate as a result of the deposition of the inactive carbon due to the methane decomposition and Woodward reaction as shown in equation 3 and 4. Beside the carbon dioxide and the methane, the biogas can also contain some impurities such as hydrogen sulfur. In the presence of the hydrogen sulfur, even at ppm concentrations, it can lead to the complete deactivation of the catalyst as a result of the sulfur poisoning. As a result, in this study, our aim is to research and investigate a catalyst that can resist the sulfur poisoning effect. In order to achieve this, we prepared nickel-based commercial ammonia supported catalysts and promoted them with yttrium, cerium, and magnesium. In figure 1, you can see our scientist process here. The first step is we solve the support material inside the water. Then we add the nickel or active metal. Then we added the promoter, which is in our case yttrium, cerium, or magnesium. Then the catalysts were calcined at 800 degrees for 6 hours, and before the reaction, the catalysts were reduced by hydrogen at 750 degrees for 1 hour. In table 1, you can see all the prepared catalysts with their weight percentage. In figure 2, you can see the experimental setup, which has 3 sections. Section 1 is the gas feed sections. Section 2 is the reactor section, and section 3 is the PC and DC section. In figure 3, you can see the methane conversion percentage. Here in the figure, you can see that the hydrogen sulfur was introduced at the 29th minute of the reaction. Before the introduction of the hydrogen sulfur, The yttrium and cerium promoted catalysts showed high temperature compared to the unpromoted catalyst. However, after the introduction of the hydrogen sulfur, there was a sharp decline in the conversion of the yttrium and cerium promoted reactions, promoted catalysts, and they were deactivated completely in 15 minutes. In general, the carbon dioxide conversion of all the catalysts were higher than the methane conversion because of the reverse water gas shift reaction shown in equation 2. Despite the decline of the conversion rate of the yttrium and cerium catalyst, this catalyst can be very promising for the future studies.